Yip from Purdue University, from United States, for those who don't know. And he will speak about some recent investigations on interfacial propagation in inhomogeneous medium. Please welcome.
So just to let you know, Purdue is from Indiana, United States. And Indiana has a name called the Crossroad of America. So nobody wants to stay in Indiana, they always try to pass by.
There's also the Who's here.
So thank you very much. That joke was not recorded. Maybe I can.
It was.
It was? No, not yet.
No.
Okay, well, thank you very much for the invitation. And so I have a nice time, and it's an excellent place historically and academically. It's a good place to be, and talking to various people. So the talk is this recent investigations on interfacial propagations in inhomogeneous medium. So most of the results that I will mention are predominantly deterministic. And even though I will mention some of the attempts that I try to investigate some of the simpler random case, okay? Because the random case in particular in this nonlinear stochastic setting is quite difficult. And in some of the workshops 1 or 2 months ago, you also have heard some related talks on these interfacial propagations. So the stochastic case is, I think it's fairly difficult to have general results. So I will mention some of the attempts in this deterministic case, but then throw in some stochastic problems. And of course, any of the problems that I mentioned, you can easily just ask yourself what happened when you have a random situation. Okay. So even in that case, the word interfacial propagations is fairly broad, and I don't know every interfacial propagations. So I will immediately restrict my attention to this interface driven by curvature, motion by mean curvature. Okay. In particular, you have an interface here. Okay. I think you can see this mouse. You have an interface. Okay. And motion law driving this interface is by mean curvature. And then there's some spatial inhomogeneity. And most importantly, we also have an additional constant, additional forcing. Okay? And we want to see how does this behavior, in particular large space, long time behavior of this interface are affected or related by this combination of curvature term, inhomogeneity, and most importantly, this additional forcing. Okay? And hence, so there's some terminology. So the normal velocity at each point, and then this is the mean curvature, and then background heterogeneity and external forcing. So our main goal is try to see what is the effective from a larger spatial scale. We don't want to see very in detail do very detailed modeling because it takes a lot of time. Instead, we want to see macroscopically what is this effective velocity. Okay? So this motion law is interesting by itself. It's geometric local motions, but it has also been used in many other modeling and applications. So the curvature is a term that tries to give the phenomena that try to reduce the surface energy. So the interface will try to evolve such that it try to become flat as possible, reduce the surface area. Okay? And F is some impurities and background or defects from the background environment. And this capital F is the external control parameters. And this kind of models has been used in many physical applications like grain boundary growth, surface evolutions, dislocation lines in plasticity deformations, and fluid contact lines, and many others, and even biological growth also. And then there's some reference you can take a look. And of course, I will also be interested in if you have any other applications in mind, then we can also talk about this too. So certainly the model that I talk about is very simple. It's local model, geometric, and in any of the real physical applications, you might want to consider non-local models, and forcing little f and capital F might come from solution of some non-local equations, elasticity equations, or diffusion equations. So, but the local models already can capture many of the essential difficulties. Okay, so the two questions that we'll be interested in is that, again, I already mentioned how to find the effective properties, and mathematically this is some kind of homogenization. So from a large space, large time, how to find the effective properties, whether there exists such a quantity, is it unique, and the stability, and how does it relate to the external parameters. So these are the key, one of the key properties that we would like to study. Another properties in this kind of evolution is that very often there is this critical phenomena that the transition between pinned and propagation states. Just like in a material interface, sometimes it won't move, but on the other hand, if you exert the forcing large enough, then it's going to start to move. So the typical behavior is that with below some critical forcing, the effective large space, large time velocity is equal to 0. And then after that, it's going to become positive. And we are interested in how it becomes positive. Okay? So physicists would like to see, okay, how to characterize how it becomes positive. There's this exponent gamma or alpha. And then they think that if you find, this alpha incorporate many information about some universal properties of the system. Okay? But also from a practical point of view, we also want to know the threshold, how large you need to exert the force such that the interface is going to move. Okay, so both the F and then the alpha are also of interest. Okay? So another interest that lead us to study this problem is that the dynamics on heterogeneous landscape. So suppose you start with wiggling, very wiggling energy landscape, and you want to go downhill, follow negative gradient flow, and then clearly from the blue line that you just follow negative gradient flow, you are not going to get down to the global minimum. Okay? Because there are lots of local minima and metastable states. So, and suppose this wiggling energy converge to a smooth energy, then clearly in this case, the dynamics of the original negative gradient flow on the original energy landscape is not going to converge to the gradient flow of the limit. And then one of the motivation for us to study this inhomogeneous medium is exactly try to tackle how to take this limit. Time, the dynamics, and epsilon goes to 0. And because the motion by mean curvature actually has its own variational structures, that the energy of the system is that the area and then some bulk term coming from the inhomogeneity. So if you look at the first variation or Euler-Lagrange equation of this energy is mean curvature that try to reduce the surface area, and then this little f is the sort of the local form of this forcing. And so it is a negative gradient flow, and then in general with arbitrary little f, there are lots of stationary solutions, and hence the energy landscape is very complicated. Okay, so of course then you might think, okay, if there are local minimum, then why don't you add noise? And of course, if you add too much noise, then you don't see this local structure of the energy landscape. If you add too little noise, then you still get stuck. So it's not so easy to see how the combination of the shape of the landscape and then the noise. But we'll see how what are the attempts that have been made in this. Okay, so after all this, then the outline is that, okay, so I'll give a very simple example in a one-dimensional case to illustrate this pinning and depinning transition. And then the idea can be extended to this semi-linear PDE case, and then fully nonlinear mean curvature flow. And then the results so far, unfortunately, is still in the deterministic periodic medium. And then I will also mention some stochastic attempts. Then after that, I will mention some recent work attempts on this study of this pinning threshold and fourth order evolutions, interface between patterns, and also this random walk in random medium, which even though it's in the simplest case, but then also exhibit many of these pinning and depinning transition. Okay, so to start out, so this one-dimensional example is very illustrative, and then the drive the what we try to study even in the PDE case. So you just have an ODE, and then this periodic potential and plus a forcing, and it's clear that when this f is less than 1, then you're going to get stuck. I mean, no matter where you start, it's going to get stuck. But when f is bigger than 1, then you have then the potential or the forcing is positive, and hence it's going to go downhill. Okay, so then then we want to study the transition between these two. Okay, so the behavior, so the transition is that we want to study the velocity, and the velocity is given by the time. So we want to compute the time from one local minimum to another, and it's very easy to compute. This is a sort of autonomous ODE, so you can do, simple calculus. You can compute the time, and then do some expansion, and then the critical time is the time you spend along this maximum, or this with a maximum slope, and you can do Taylor expansion. And near 1, when f is near 1, the dynamics dx dt is given by x squared over 2. So that's the sort of like the normal form when you try to compute this near the bifurcation phenomena near the critical threshold. And then after this simple calculus, you will see that the velocity 1 over time is exactly delta to the power 1/2. So we have this scaling 1/2 to the exponent. And this is purely come from the periodicity of the environment. Okay? And then this ODE case, this kind of analysis, even for random potential, has also been analyzed very carefully. So I will mention this later. So this is a simple ODE case, but then it has also been this idea has also been used in some discrete system in in a PDE, but discretized version of PDE. So you have a bistable type reaction diffusion equations, Alan Kahn. So you have this is bistable type in the sense that this W of U is equal to, so the shape is like this, and the stable states are -1 and 1, and since it is a stable point, so the solution will roughly behave very like -1 and 1, and hence there is a front. And we want to see whether how does this front move. Okay, so then also in this dislocation motion, there's Franco-Kontarova type models, and also for this charge density wave for electron interactions on the metals, they also have a similar kind of equations. And the interesting thing is that for the continuum case, then we always have when there's external forcing, there's always a traveling wave equations, traveling wave solution when C is positive for any kind of tilt. But then when you have a discrete systems, then you have a propagation failure such that in the sense that the front is not going to move even if you have a forcing, and this is because of the presence of stationary solutions. And for in some asymptotic regimes, that Kiner, Bonilla, Carpio, and Fisher has studied this type of systems, and essentially the idea is basically a one-dimensional case. Even though it is a infinite dimensional discrete system, in some asymptotic regime, they can use this one-dimensional case to analyze this deepening transition of this front. Okay, and then in the random case, okay, so you can also easily think about, okay, what if we add noise? So in the first order case, correspond to a high friction, then you have this original deterministic and plus a small amount of noise. And you can also consider second order case with inertia effect, that with small mass or high friction, that you can also add noise. Then you want to see, as I say, you don't want to add too much noise, otherwise you wash out all the local behavior of the potential. So the limit of a small noise or small mass has been studied quite carefully. In various forms. Riskin has very careful analysis, for first order and second order in the small noise limit, and then Wenzel, Fredlin, Wenzel, and Hera and Pavliotis also have studied these long-time behaviors in terms of diffusion coefficients when various parameters goes to 0. But most of the results are when there's no tilt. The effective behavior as a function of f is still need to be understood more carefully. And now I'm with the student, I'm trying to understand some of the techniques of this. And many of these results are still in one-dimensional case. And in the two-dimension, then even though people can prove the asymptotic limits exist, but then it's very hard to compute the quantity. And that's here what we like to do. And in the two-dimensional deterministic case, I will just mention that Menon has a result and also it's only for 2 dimensions. For gradient flow. But in general, how to compute quantitatively the effective velocity as a function of f still need to be understood more carefully. Okay. So then with this ODE setting, then let me just go to the PDE setting. So as I say, the setup is sort of bifurcation. Then, okay, so if you look at a book of a bifurcation, usually there's an abstract framework, then with various assumptions. So let's just write down the assumption, then see how we can apply to actual situations. Let's assume, so here is this dxdt is a nonlinear term plus forcing. And then let's assume with some forcing small enough, there's a stable stationary solution. Okay? And then at the critical threshold, then this stationary solution just becomes unstable. Then at the behavior, dynamical behavior at the unstable point can be done by the standard manifold analysis. And for second order type equations, then the standard manifold is one dimension. Then you can write down the dynamics of the position on the standard manifold in the following form. And again, this is sort of like the normal forms, dx dt, and the first term is this s squared. Okay? So that is the sort of like a typical dynamical equation at the bifurcation point. So this is abstract framework, but we can apply this to actual the front propagation with some simplification. So then the first is this pinning and depinning transition for this linearized version of a motion by mean curvature. Okay, so now I write everything as a graph. Okay, u sub t is equal to Laplace u, and then this is inhomogeneity, and it's periodic. So these are colors just represent different values of the inhomogeneity. And then there is external forcing, which is what we want to study carefully. Then let's assume f is periodic, and then under some general generic condition, we can actually this assumption can easily be satisfied that when there's no forcing, then there's a stable stationary solution, and then at some critical threshold, then the equation becomes non-degenerate but lose its stability. So these are sort of generic conditions. So it's easy to it's fairly easy to satisfy. And after that, then we can apply the bifurcation techniques that we studied earlier. That okay, so this is a restate. Below the pinning threshold, there's a pin state, and above there's a unique pulsating wave. And since it's a space-time periodic, the environment is periodic, so we don't look for traveling wave. Instead, we look for pulsating wave. So it's a periodic in both space and time. And then the scaling of the velocity, okay, then it's exactly satisfy this kind of a one-dimensional type ODE bifurcation setting. Okay, so even though this is slightly more linearized version of the fully nonlinear motion by mean curvature, but then we expect that this can be done even for the fully geometric motion. Okay, and in particular, this scaling velocity is equal to the critical additional forcing to the power 1/2, which come from the periodicity of the domain. Okay. And then we also apply this to another type, is a front propagation, the bistable type. And so, of course, there are many other front propagation, for example, frame propagation, KPP type, which the phenomena will be different. They don't need a critical, there's no critical threshold. But here we do have a critical threshold because of the bistability, and the front itself is very stable. So again, this is a double well potential. And then in general, the front shape will have a 1 and -1, and then there is a front location. And we want to see how to study the dynamics of the location of this front. Okay, so then with a spatial inhomogeneity and with additional forcing, then we can also apply the similar techniques. Say that below some critical threshold, there's a pin state, and above you have pulsating wave space-time periodic solutions, and then scaling also apply to this ODE setting, which is in this case we also have quite explicit formulas, and that's the key. We not just want to know a general theorem, but the explicit computation is also of interest. Okay, so these are the pinning and depinning transition in some simplified version. Okay, so then the next I'll get into this fully nonlinear inhomogeneous motion by mean curvature, and then of course the equation looks like a mess. But okay, so let me briefly explain. In the graph, if you write down in the graph, so this will be the mean curvature term, and then this is the inhomogeneity. And the difficulty of this equation is that there are two parts. One is that this elliptic operator is divided by this gradient, and hence it can potentially become degenerate. And also, because of the geometric motion, we want to add a normal velocity in a normal direction, and this gradient also multiplied to this f. So if you have all of these terms, all these correct terms put together, then this equation is highly degenerate and nonlinear, and graph in general will not stay as a graph. Okay? So in general, you cannot. Of course, there are many works that simplify some of the situations that you omit some terms so that you have nicer behaviors. But in general, for the original problem, graph in general will not stay as a graph. Okay.
Question. So, if graph does not stay a graph,
yes,
do you need some different description of?
That's right. Yeah. So that's the next slide.
Sorry.
So there will be there are other methods. You can study motion by mean curvature. Of course, extending the situation out of a graph situation. Okay? So the first sort of a robust measure theoretical weak type of definition of motion by mean curvature is done by Brackley. It's a very full definition and make use of some sort of technical definition of a geometric measure theory. But that is the first fundamental definition of motion by mean curvature. And later on, even though there are various other approaches to study motion by mean curvature, they always try to compare their results with the original definition of Brackley. So Brackley's very full definition sort of give you a benchmark. The definition, I would say the D definition of motion by mean curvature. Okay, of course, in the graph case, under some assumption by Ecker-Huiskin, they have used purely PDE techniques, restrict the attention in the graph. And then without the graph case, then you have this level set formulation, and it is given by this form. And then the level set formulation is, I want to keep this double well potential. Is that, okay. So you have frame propagation of front, so this is gamma, and is equal to xt is equal to 0. So the level set of u is positive and u is negative. Okay, and if you write it in using this level set formulation, then the equation becomes even more singular. You can divide by gradient u, and then so it's extremely singular. And nevertheless, there's this because of the second order and the presence of maximal principle, then there's this viscosity solutions that people can use to tackle this. And then the first result on this is by Evans, Broke, and Chen, Giga, Guto. Then of course you also have this diffuse interface, in the sense that instead of a sharp interface, then you look at construct a function such that it approximates this, and that there's a thickness of epsilon. Okay, so this is diffuse interface. And first, formal or more careful formal expansion is done by Keller, Rubinstein, and Sternberg, and the equation is given by this, and because of the bilinearity, that this function phi will become 1 and minus 1 quickly, but then make a rapid transition. And of course, the key is to understand as limit, in the limit as epsilon goes to 0, what happened to this diffuse interface. And that has been shown in various form, in various rigor, that it will converge to motion by mean curvature or inhomogeneous motion by mean curvature. And there are also, of course, with the workshop last few months, there are also many works to extend many of these to the stochastic case that I have done early on. I also have some work on this stochastic motion by mean curvature using variational approach. And then Fanaki also have some results on this asymptotics for this diffuse interface. Then recently this Weber also have extended some of these results, and then Leons and Soukhanidis and so forth have this viscosity setting. So many of this work has also appeared earlier. But in general, in the stochastic case, right now, either you look for weak solutions that exist, but then the strong classical solutions right now is still lacking. Okay, even though there are various techniques you can tackle this problem. Okay, so this is the fully nonlinear case. Then, so for the let me go back to this picture, fully nonlinear motion by mean curvature. So even right now the setting we have is that for the graph case, but I'll explain a little bit why this is. It's not just a technical restriction, and in general, as I say, graph will not stay as a graph, so that in general, it's not clear how to tackle this. And actually, without any assumption, so far the homogenization or limit problem of this inhomogeneous motion by mean curvature is still not clear how to write down the limit equations without any assumption. So all the work so far requires some simplification in various settings. Okay, so our setting is that with this. Okay, so suppose in the previous picture you have a front in inhomogeneous medium, then the medium will require it to be periodic, and then but then it needs to be small, weakly periodic. The forcing, the size needs to be small, so weak heterogeneity. And in that case, then for any macroscopic direction, for any direction, okay, including rational and irrational, we can actually prove the existence and uniqueness of an effective speed of propagation. So this property actually can exist under in this setting. And then further, the speed is also a Lipschitz continuous with respect to the normal direction. Okay? Then the long-time behavior and also can be described by this pulsating wave. So we can prove the existence, uniqueness, and stability of this pulsating wave. Okay?
I mean, is that consistent with the speed of propagation? The pulsating wave doesn't move, right?
The pulsating wave does move. Yeah. Well, it's space-time periodic, right? It does.
Yeah, but you know, it doesn't. Pulsating to me means that it just is periodic.
Oh, that's okay. Yeah, right. Strictly speaking, it doesn't. It's just periodic in space and time. But I was
like a sine curve, you know, would move and it's.
That's right. Okay, let me just quickly show you a picture of what I mean by pulsating wave. My definition, pulsating wave may be slightly more generalized. Pulsating wave is that start a time, the solution, after some time, some definite amount of time is moved up in space, but then also shifted a little bit. So there's a time shift and space shift. And time shift and space shift are related by certain properties. So these are what I call pulsating wave. Yeah. So strictly speaking, yeah, periodic things don't move, but then here, when I say pulsating wave, actually it will shift in space. Yeah. Because of the additional forcing. Yeah. Okay, so in general, so then in this fully nonlinear case, we can actually in fact prove the existence and uniqueness properties of effective speed of propagation and some continuity properties. Okay, and the key of this is to try to prove the uniform space-time oscillation and gradient bounds, and hence the things will remain as a graph. Okay? All of these sounds very restrictive, remain as a graph, but then I will show you that in case when the graph solution is not true, then many other complicated things can happen. So now let's just restrict to the case with the graph for the moment. Okay, so then the key is that to establish a uniform space-time oscillation in appropriate moving frame. So what do you mean by space-time oscillation? In the sense that, so here is front, the curve, and then the oscillation is the maximum minus the minimum. So this is what I call the oscillation. Okay. So if this oscillation in some moving frame is finite, independent of time, that means that there is an effective front. So otherwise, if the oscillation becomes larger and larger, then it is not immediately clear how to define the front, okay, which I will show you some pictures. And then this is the key. And once you have this, then slightly more, of course, this is degenerate. We need to have a more careful analysis. But then this is the key. Once you have the oscillation, then many of the results that I mentioned will follow quite naturally with a careful analysis. So let me just give a brief word of what do I mean. So this is the pulsating wave that Professor Mueller have just asked. That we can show long-time behavior actually are described this converge to this pulsating wave. Okay, so then the next I will just quickly say how do we prove the uniform oscillation bound, and then we make use of this Birkhoff property. This property, we prove this property in this dynamical case, and with this property, then we can reduce the behavior on the whole space to a finite dimensional space. That okay, so what it says is if you start with a planar curve, okay, and in any direction, and when you move after some later time, then if you have cube on top of the front, then if you do sort of tangential, I mean not strictly tangential, but you need to move up and down because of discreteness, any tangential movement of this cube will also lie on top of the curve. And similarly for the cube below this. Okay? So because of this, then the oscillation, so this kind of thing cannot happen, that you cannot have a small oscillation and then suddenly large oscillation. Okay? So essentially oscillation on the domain, infinite domain essentially can be controlled by small domain. So this situation is not going to happen.
See, I'm having trouble seeing how you could have oscillation in this context. Doesn't it have a tendency to flatten out?
But you have spatial inhomogeneity.
Right. So can you draw a picture?
Sure, yeah. There will be lots of pictures later on. In the sense that suppose there is an obstacle, and the front is going to move, and then suppose there's a forcing, and then this is going to start to move, and this obstacle has will try to block this, and then this is going to bend around. The curve is going to bend around. So there are many oscillations like this.
Well, but that's just a static situation. How does that result in oscillation?
Okay, I will show you more pictures later. Yeah. So this actually the oscillation will come in because it's a combination. How strong? Okay, if the curvature is strong, then of course it will has cut through the obstacles.
Right, and so it's.
But if the curvature is not strong enough, then but if by increasing this f, then what the curve will do will just move up in some other parts with in the region without the obstacle, but then you will loop around this. And then after that, when you encounter a second obstacle, then similar things will happen. Yeah. I will show you pictures.
Oh, okay.
Yeah.
I don't see how it would get below there again. Which you would have to do to oscillate, but anyway.
Yeah, yeah. It will be clearer with all the nice pictures that I draw later. Okay, so but this is the Birkhoff property that we had we use. Then okay, the oscillation the analysis from infinite domain can be reduced to finite domain. Then after that, then careful analysis because it's still degenerate equation, Bernstein techniques that we can bound the gradient by oscillation and oscillation by gradient. And then through some iteration scheme that we can have gradient bounds and final oscillation for all space-time. Okay? And these techniques actually has been studied for the stationary case by Cavarelli, Dallalev. They study the plane, what they call, whenever you have an interface with a finite oscillation, they call it plane-like minimizers for minimal surfaces in periodic medium. And actually they, for the static case, they show this, and then we extend this to the dynamical situation. And in fact, the dynamical case, the situation is actually easier to prove. Okay, so then, okay, so with that said, so these are the two type of results. One is the deepening transition, and one is the effective behavior in the fully nonlinear setting. So let me just mention some results that on this homogenization. So this is the level set formulation for motion by mean curvature in inhomogeneous medium. So as I say, in general, without any assumption, how to homogenize this as the limit as epsilon goes to 0 is still not known. Okay? So we need certain assumptions need to be imposed. So various relevant work is Cavarelli, Suganidis, and Wang. They study fully nonlinear but uniformly elliptic equations, which does not cover this case, but they can handle periodic and random case. They can find out the effective, limiting situation. And Patachara and Creation, they study also this situation under various limiting regime, first order Hamilton-Jacobi equations or second order curvature flow, under the assumption of the existence of a cell problem. And our work basically provides a solution to this cell problem. And Leon and Suganidis and studied the mean curvature flow in periodic, also random medium, but their setting more or less will require the forcing to be positive. Okay? And our setting, the forcing is general, but need to be small. Okay. So okay, so now let me emphasize a bit more why this forcing need to be small. If the forcing is not small, as in this case you have lots of obstacles, the interface is going to move, and when it starts to move, as exactly in this situation that this obstacle is very strong, but the interface is can move around, and then after that it's going to pinch off. after it pinch off, then it's going to leave some remainder behind. But then if this obstacle is still strong, then the curvature cannot shrink it, cannot make it disappear. So in this case, it looks like, okay, so then you might think, oh, why don't we just take the top one, that's our interface, then forget about what's shattered behind. But on the other hand, I would say, from the next example, you will see that it's not so clear how to do this. Suppose the obstacles are strong, but not too strong, then you have this fingering phenomena that, okay, so then this is strong, but then the interface will still tunnel through, but then it's not strong enough to pinch off. So there are still, I mean, some kind of a pseudo part left over. So in this case, it's not clear how to define the interface. Okay? And exactly, this is the situation that the oscillation does not stay bounded. If things keep on going like this, then the oscillation is become longer and longer, larger and larger, so that how do you define effective interface is not immediately clear. So these two situations are not too much different, I would say, for my understanding. Then, okay, so actually, in fact, it's much easier to generate any examples. It's not, you don't need to have, you don't need to put in any complicated obstacles. Even in the laminate materials, if the materials only depend in one direction, then you can easily construct, like in this mean curvature flow, you can construct sub and soothe solutions to force this oscillation, increase of oscillation of the front, and hence the oscillation will not stay bounded. So it's not clear what is the effective front. Okay? So that's why there's difficulties in this case. And then, of course, people also have realized this. So it's not clear in general, how to do the homogenization. And hence there's a classification by a work done by Kataliaklios and Stochastic. You consider a general fully nonlinear degenerate elliptic PDE or parabolic PDE. So there are three scenarios can happen. The first scenario is that the homogenization will really take place. So that there's a limit, and the limit solve a limiting equations. Okay? And then the pinning or trapping occurs, the solution gets trapped, then that means that the solution will not move. U epsilon, the solution will converge to the initial data. And then what they call homogenization does not take place if the lim sup and lim inf, they don't equal to each other. Okay? And actually, this is the situation that I draw here. I mean, there's a positive part and negative part, then it keeps oscillating. Then, of course, you can ask for weak convergence, but in weak convergence, then you need to ask for the front in front of different kind of phases, not just pure phases, okay? Which I will also mention some of the attempts later. Okay, so these are, three kinds of situations. Certainly the last kind is the most difficult. How do you define the effective front? And if you want to have, really want to have a homogenization result, it seems based on the results so far that there are two dichotomy of conditions. Either you require positivity of the forcing or more or less positivity of forcing, or the forcing to be small, so that you can actually derive the homogenization results. Okay, so these are the periodic setting, and then in the random case, and I believe you also have heard the talk by Nicholas Steer a month ago and so forth, and I think probably earlier. Then in the random case with random potential, then certainly it's much harder to prove things rigorously. But Nicholas Steer and co-authors can manage to prove the existence of some pinning threshold under this kind of, for this linearized equations in dimension 1 and 2, there exists a forcing below that such that there's a stationary solution. And above, then there's no stationary solution. So sort of like there's a transition between pin and depinning. But then the exact transitional behavior still need to be analyzed.
Is the top equation linear because you use
semi-linear?
Semi-linear.
Yeah. So F is depend on X and U, and then omega is random, and I think the random is sort of independent random field. Some smooth version of independent. Some random field. Yeah. So that's the result that they have. Okay. Then from there's in the physics community, there's some simpler model, sort of like a mean field type, that they replace the Laplacian. What it means is that you look at the local average and minus itself. That's the Laplacian. but this is again is a bit hard to do analysis. So there's some simplified model in the physics community that they can do more careful analysis. Is that they replaced by Laplacian by this long time average or mean field. So instead of looking at the local average, you look at the average of the whole space and minus yourself, and then there's some random forcing here, or random inhomogeneity, and they can compute pinning threshold and depinning transition quite carefully. But this is certainly much simplified situation. Okay, okay, so that's the about this effective behavior. Then the next. Before I go on to the next section, I will just quickly say, because when we do homogenization, there's also depends on how large the space scale and how large is the time scale you look at. So this is the original equation that I wrote down. Then in fact, this is the cell problem of the following motion law. So epsilon times kappa, and F is the forcing is order 1 and kappa is order epsilon in the size of epsilon. This is the most difficult and most interesting scaling, because both the curvature and the inhomogeneity are put together in the same problem. And some other simplified version can be done in the sense that if in the original problem the curvature is very, very small, so that it's given by a first order information, or the forcing or the curvature is very strong, so that everything is lying very, very flat. In those cases, then you can do fairly explicit computation.
What does the cell problem
mean? So if you solve a periodic problem, homogenization in periodic domain. Okay. So then you want to see the large space, large time behavior. Then you want to construct local or building block solution in each cell, and then you paste them together. And then the large space, large time limit is in the sense that you let this cell size goes to 0. Okay. So the original problem, the interesting case is when both curvature and F are of the same order, so that they can affect each other. And after you rescale the size, then it becomes epsilon kappa here. Okay, so that's the rescaling. And under this rescaling, then you can have this first order Hamilton-Jacobi equation. Okay, under this sort of like a hyperbolic space-time scaling, can get a first order Hamilton-Jacobi equation. Then of course, in principle, you can also ask for longer time scale, diffusive time scale. Then in that case, the space scale is still remain the same. You want to have both curvature and inhomogeneity live on the same scale, but then the time scale is much longer, then it becomes this equation. So in principle, in here, the curvature term will become much, much stronger. So in principle, in the limit, you get some kind of a second order equation. But this is still far from clear how to do this. But I think this is very interesting to see. So the reason why it is clear is that you have one kind of a pattern in one direction and another pattern in another direction. These are interfacial patterns. And how do you merge them together and to define the effective notion of curvature in a heterogeneous medium, then that is also not clear. Okay. So that's the additional problem to think about. Okay. So then the next is this pinning threshold. So we look at the effective medium, then let's go back to this pinning threshold. As I say that for practical matter, it's also important to know how to compute the pinning transition, the value of the pinning transition. That recall the phase field model, this reaction diffusion equation, when this is a bistable type, there will be a traveling wave. As long as you add a little f, there's always a traveling wave. Okay? But then for discrete version, this is not true. As I mentioned in the earlier examples, that the discreteness automatically gives you lots of local minimum for the discrete energy landscape, and he will block the space, block the front from traveling. Okay? So then, there are works that people try to compute explicitly this depinning transition, this value of this threshold in some simplified examples. For example, this two-dimensional discrete Allen-Klein equation. So this is the discrete Laplacian, and here is a nonlinearity, which is a bistable type, derivative of a bistable type, and hence the nonlinearity becomes like this one. Okay? Not like the KPP. KPP, then f of u is strictly positive. Okay, so then because of the discreteness, then it's going to get pinned, and then there is a bias. We can add some additional forcing to this discretization, and this bias is given by this A. If A is 1/2, then you have a symmetric bistability, but A is when you deviate from 1/2, then you automatically give you some bias. So this is a very generic model to study discrete system in bilinear potential. And they choose this special kind of bilinearity so that they can perform explicit computations. That they look for traveling wave. So I will skip a few slides here. They look for traveling wave, and then once you have a traveling wave, the crucial quantity is to compute is the speed. Okay? And they also have explicit formulas. They can compute the speed, and then they plot out the speed and the transition. So here is I think the graph is plotted sort of like we need to tilt it 90 degrees. So the vertical is the speed, the horizontal is the speed, and the vertical is the tilt, or the biasness of the discretization. Then you see that when the bias is not strong enough, then there is a tilt, there is a pinned solution. And after that, then the velocity is going to become positive, and then there's a pinning and transition here. And because of this specific type of nonlinearity, then they can compute this pinning threshold explicitly. And the interesting thing they have found out is that this depinning transition, this pinning threshold, is very wildly behaved. It is continuous and equal to a constant at irrational direction, and it's discontinuous at the rational directions. Okay, this phenomena. Recently, Malay Paré has also extended this understanding, and seems like he can show that for discrete system, this is more or less sort of universal. Okay, and then we also try to mimic some of the computation that we try to consider a continuum case. Continuum situation, then with a small inhomogeneity, then we can do some linearization. Then depending on then we can try to see how does the deepening threshold relate the angle of the interface. Okay, so this A and B are sort of the angle, represent angle. A is the cosine theta, B is sine theta, and then we can perform asymptotic computation. And what we found out is similar to the previous case. Like the pinning threshold actually behave quite wildly at the rational angles. Let's say, for example, that when the angle is 45 degrees, then the pinning threshold can be quite explicitly computed to be of order delta. And then when it is 90 degrees or 0 degrees, then it is of order delta square. Then some other more complicated angle, depending on the denominator of the rational value, then it is much smaller value. So it seems like at each rational angle, then the behavior of the pinning threshold is much more complicated. Okay, so this is the some attempts on this deepening transition. And of course, if you look at random case, then if the random material is isotropic, it seems like then the pinning threshold will be independent of the angle. Okay. So then the next so with the remaining time, I will mention some of the recent work that I've also done in this regard, and also as this work is and also done very recently, and thanks to Newton Institute, Nicholas was able to stay here for a few days, and then we actually have done some work, try to extend some of the earlier results on motion by mean curvature. And one of the techniques for mean curvature is that it's a second order, that we can have maximal principle. So you can use maximal principle, try to construct sub and source solution to prove estimates. But if you have a fourth order equations, for example, surface diffusion in the following case, so the Laplacian U is the linearized version of mean curvature, and then the bi-Laplacian is the linearized version of the surface diffusion, which is fourth order, then plus the inhomogeneity and forcing. So we expect that if this fourth order is small, then the behavior will be more or less similar to this second order case with the same pinning and deepening transition. But in general, then the pinning and deepening transition will be quite completely different. In particular, if you look at these fourth order equations, bi-Laplacian heat flow, ut is minus u fourth derivative, then if you look at this function minus x fourth, even though this minus x fourth has a local maximum, but then actually under the bi-Laplacian heat flow is going to go up. So the by motion by mean curvature, if you have a local maximum, the mean curvature is going to let it reduce motion by mean curvature. Okay? But then if you have a fourth order, for this kind of initial data, actually is going to continue to move up. So that you don't have a maximal principle, then there might be some kind of tunneling phenomena. And then this phenomena, this kind of argument has also appeared earlier, Giger and Ito. They show the laws of convexity and embeddedness for curves under the fourth order flows. And then we actually also use this example to construct, to use this explicit computation to construct an example such that you have this tunneling phenomenon. So this, in this example, is that we construct inhomogeneity such that this is a 0. It is a 0 along certain level. If the inhomogeneity is strictly 0, then the second order equation will give you a super solution, just block any propagation. But because of the fourth orderness of the equation, this solution will actually go up. So initially, it's going to go up, tunnel through this pinned solution, and after that, then we can just arbitrarily construct some forcing, try to continue to pull it. So in a way, in this case, that we can have a coexistence of pinned and propagating solutions for fourth order equations. So it's not, then the concept of a pinning threshold is not immediately clear, or maybe we should look for a pinning interval such that there is a coexistence of pinned and propagating solutions. Okay, so so this is one. And then another is that the boundary between patterns, as I say that in general, in the case, we don't have a concept of effective front because the oscillation of the front will go larger and larger. So then we can look for weak convergence. But then when you look for weak convergence, then we need to look for a new type of interface, the interface between patterns, two kinds of patterns. And then if you look at a discrete system or spin systems, very often you might also have, because of inhomogeneity, you have lots of you have a new type of patterns, and then two kinds of patterns, but then the real interface you look for is actually the boundary between two different patterns. So this kind of, I think it comes out natural, not just the interface between two pure faces. And this kind of ideas also has been appeared in various works in the stationary case that dear Lucia Navaga and dear and Orlandi has considered this gamma convergence for this Elegant functional with oscillatory but random and also random forcing. Try to prove the gamma convergence should try to derive some effective interface between patterns. And then the discrete system, Alejandro, Brides, and Chichelis, they look at this phase and antiphase boundaries in these binary discrete systems. And very importantly, they study this nearest and next nearest neighbor interactions. So maybe you can help me to pronounce the name, Marco.
I would run into larger difficulties if it would be Chinese names.
Okay. So they study this nearest and next nearest neighbor systems. They really construct examples in the stationary case that they can have a patterns and boundary between patterns. And of course, from a discrete or dynamical systems point of view, they have cell dynamical systems that they study lots of this kind of different evolutions between patterns. And so, but here I will mention one recent attempt that make use of this nearest and next nearest neighbor interactions. Okay, so then, so this lattice model, then the nearest neighbor interactions, for example, if you have this ferromagnetic type, in the sense that if the spin at a location want to behave as much as the next your neighbor, then you have the minimizer will become pure phases. And you have anti-ferromagnetic. If you want to behave oppositely, then you have checkerboard phases. Okay, so these are nearest neighbor. But if you look at a next nearest neighbor, then combination of a nearest neighbor and next nearest neighbor, then the pattern is become much more complicated. I mean, it's still manageable, but it's much interesting is that you can have checkerboard phases, stripe patterns, and of course pure phases, and this combination of this. And hence, the more interesting thing in this case is look at the boundary between these kind of different kind of patterns. And it is joint work in progress with Brides and Chichelis, is that we try to study the dynamics of fronts, actually in this between patterns, using some discrete space, discrete time variational methods. And we show that this is going to converge some kind of crystalline motion by mean curvature. So this is the front, not just between phases, but between patterns. Okay. So okay. So then the next. So the time. So as I say, in the truly PDE case, then it's fairly difficult to have a rigorous result. So recently, I also get interested in this random walk in random medium, and there are some by classical results. It's also clear that there's this pinning and depinning transition. Okay, and the first work, sort of in this setting, is by Solomon, probably his thesis. He looked at this random walk with the hopping rates is independent random variables, and depending on the statistics of these hopping rates, then you can have convergence to infinity and negative infinity, and these are the transient states, and these are the recurrent states. But we are more interested in the quantitative computation, which has also been done in this case, that Solomon has do explicit computation for the effective velocities in various settings, and in the critical parameters, C9 and Custon, Kozlov, and Spitzer, and has characterized at the pinning what happened if you want to do more careful scaling. What are the statistics of the random walk? They also have been done. These are classical results, and then K has extended some of these to the hopping rates that you can hop to longer neighbors. But in that case, then the computation becomes much more complicated, and we would like to study more carefully how to analyze this, do some explicit computation. So that's so we look at this work by the Ritter. He actually has an explicit computation. You do periodic. You assume the medium is periodic and compute the behavior, effective quantity, and let the period goes to infinity. But this the computation is done only for the nearest neighbor. Okay, so we try to extend this, see what kind of a function can be done for the next nearest neighbor. So in general, of course, there's no explicit formulas, but so that we do some asymptotic computation, so that there's some small amount of hoppings to the next nearest neighbor. Then by asymptotic computations, then we can have compute the next order term, and we actually has plotted out in the sense that. So this is the first order without the nearest neighbor hopping rate, but then with the nearest neighbor, next nearest neighbor, then the correction term sort of behave in the blue line, in the red, in the yellow line, and then we still try to understand this kind of formulas more accurately.
Sorry, what do the axes represent?
Axis is this alpha. This alpha represents the randomness.
That's the horizontal?
Horizontal, yes.
And what's the vertical?
It's the velocity. Okay, so in here we want to understand how does the parameter of the randomness affect the effective velocity. Okay, so this is alpha. When alpha, so this is just the nearest neighbor, and then after this there's a purple line. That's the analytical formula, and then when alpha changes, then the simulation matches with the analytical formula, and then the yellow line is when we add on top of the nearest neighbor, next nearest neighbor hopping rate, the correction term. Then the final slide is that okay, so this for the discrete system has this continuum analog. Is that the Brownian motion in a Brownian potential? That the potential itself is actually Brownian. Then this Kawazu and Tanaka actually analyze this very carefully, and then this is a Brownian potential with a tilt, with kappa. And by using this exit time analysis, they can have Kawazu and Tanaka actually can compute quite carefully what is the effective velocity. So, and then here the depinning transition is the picture is similar, but then the transition exponent is completely different. It depins in a linear fashion. Okay, so this is and this result is very explicit, quantitative for Brownian potential, and there are some extensions. And certainly it will be also be interesting to explore this pinning and depinning transition for a larger type of random potential. See how this is changed. And so, of course, if you have any ideas on related work, then certainly I will be interested in discussing with you. And with that said, and thank you for your attention.
Questions?
So even with the pictures, I didn't see how there could be an oscillating solution.
Well, okay. Let's say, okay. You can, okay, just look at this. Look at the top one.
Okay.
So let's say suppose the obstacle is not too strong. So then when the loop wrap around the obstacle, the curvature will shrink it. And hence, after some time, then this part will disappear. Because the curvature will overcome the not so strong obstacles. Then after that, this will disappear. But when this disappears, this move up and a new one will appear. So the new one keep appearing, but the old one keep disappearing. That's the oscillation, space-time oscillation solution. Yeah.
More questions? Thank you.
Thank you.